All right, everyone. So in this video, we're going to be talking about VSEPR theory, okay? VSEPR, which we pronounce as VSEPR, okay? This is what it sounds like, VSEPR, when we say it out loud. But really, the initials are VSEPR, which stand for Valence Shell Electron Pair Repulsion Theory. Yikes. I'll write that down fast, okay? Okay, so we have valence shell electron pair repulsion theory, aka VSEPR, okay? And what this wonderful thing means, okay, is basically right here, okay? Electron pair repulsion, right? Electrons repel each other. Here's an electron. Here's another electron. If I try and squish them together, they're like two magnets that are facing the wrong way, right? They're going to repel. They're going to try and stay as far away from each other as possible. Okay, so electrons are going to try and stay away from each other. They're going to repel each other. And we're talking about electrons in the valence shell. So in your outermost shell of your atom or molecule, okay? And what this is going to tell us, what VSEPR theory is going to tell us, because electrons don't want to be near each other, okay, and because these are the electrons in the valence shell, aka my bonding electrons, all right, VSEPR theory is going to tell us what shape my molecules take. Okay, so in order to visualize this and hopefully have you get it with our notes, I do actually want you to make kind of a table, okay? So your table is going to be 7 columns across, okay? So just so you can kind of plan ahead, right? If this was your binder paper, you're going to want to make 7 columns. So the first 6 can be kind of skinny. 1, 2, 3, 4, 5, 6. Okay, clearly I drew this not great. Okay, but you want your 7th one to be kind of bigger because that's where we're going to actually be drawing the shapes, okay? So here are going to be your kind of 7 columns, all right, on your binder paper. Now, obviously, I'm taking up a lot more space and I'm going to take up a lot of pages doing this because, well, because I write huge. Okay, so we are going to have your first column is going to be number of atoms bonded to your central atom. This is actually really important. Okay, so bonded to your central atom, number of lone pairs on the central atom. Okay, total electron groups. Again, this is going to be on your central atom. This will make sense. Electron geometry, molecular geometry. We're going to do, an example of a real life formula that has this kind of stuff. And then we're going to draw it out so that hopefully you will see it. Okay. Now I also bought some styrofoam balls and toothpicks to try and help you visualize all this stuff. So I'm not sure how this is going to come across on a 2D video with 3D shapes, but hopefully we'll be able to kind of see it in our minds. Okay. All right. So if I was going to start out, okay, imagine there's 2 atoms, okay? Let me open up the toothpicks here, all right? And I was going to bond these 2 atoms together, okay? Sorry for the weird styrofoam sound. Awful, okay? There. I bonded these nice 2 atoms together, okay? These have to be linear, right? This has to be linear. There's no central atom. There's no way that I can get the electrons that are bonding between atom number 1 and atom number 2 to be any further apart, right? There's 2 atoms, that's all it could possibly be is linear, okay? So when we actually start talking about VSEPR model, okay, the kind of minimum that you need is 3 total atoms, okay? You're not going to be talking about 2 because there's no central atom here, right? What's the center? There is no center. It's just atom 1 bonded to atom 2, okay? You need a central atom. So the easiest possible, the most simplified way that we can do VSEPR, okay, would be to add 1 more atom. If I was going to, all right, add this other atom, and this is going to be my central one. Maybe I should color it. Okay, there we go. My beautiful coloring here on my styrofoam ball. This is always going to be our central atom, okay? So if I was going to add another atom is going to bond to my central atom, okay? What VSEPR tells us, right, is that electrons repel each other. They don't want to be near each other. So if I put this atom and attached it right here, okay? Now these electrons from this atom right here are really close to these electrons on the other atom, okay? These guys are really close. They repel each other. They're going to try and push each other away. So this atom's gonna be like, oh no, man, way too close to here. I wanna get away, get away, get away, okay? Until it goes all the way as far away as possible from the valence shell electrons that it's around, okay? If I went a full 180 degrees, right, full linear, now the electrons here and the electrons here are as far away as possible as they can get from each other, okay? If I went even further, right, if this guy went further this way, now he's coming back towards this original atom, this first atom. So again, these electrons here and the electrons here are going to repel. Okay, they want to be as far away from each other as possible. So the easiest possible example for this is if we have 2 atoms bonded to my central atom, right? This is how many atoms are bonded to the central. It's not saying how many total atoms, because total atoms would be 1, 2, 3 total atoms. Right, I'm saying how many things are bonded to the center. 1, 2. So I have 2 atoms bonded to my central atom. Okay, how many lone pairs? So far, 0. This will come into play in a little bit. Okay, but we're trying to do the easiest examples first and build from there. So now total electron groups. This is where it gets somewhat confusing-ish, okay? Hopefully it's not confusing when we break it down, okay? You might get a question saying, what are the total electron groups on the central atom? Well, in that case, you're just looking at how many directions do electrons go around my central atom. Well, in this case, I have electrons here, okay? So there's 1 electron group, and I have electrons here, 2 electron groups, okay? This total electron group should be these 2 numbers added together. All right, so total electron groups should be 2 for this guy. Okay, so now what is the geometry that my electrons take around my central atom? Well, I've got electrons here and electrons on the full other side, 180 degrees. Okay, this is going to be linear. Okay, these electrons are linear. It's in a line, right? And in this case, my molecular shape is the exact same as my electron shape. This is not always true when lone pairs come into play, okay? But what shape does my molecule take? So now you're looking at the atoms, not the electron groups, right? But the atoms. So my atoms are in a line. They are linear, okay? A nice example in real life of a linear molecule is carbon dioxide. When you exhale, okay? Carbon dioxide is a linear molecule, and we can look at that, okay? If we were going to draw out the Lewis dot structure for carbon dioxide, right? Hopefully we're feeling really good with drawing out our molecules, right? And this is why I want you to be so solid in drawing them out first, right? Drawing your Lewis dot before we start to try and get into crazy VSEPR theory, all right? Because if you don't draw out your molecules correctly, no possible way that you're going to be getting your shapes correct, all right? So carbon's going to be in the middle, right? Maybe I should take the time. Okay, carbon has 4 valence electrons. Each oxygen has 6, right? So carbon's going to double bond to an oxygen, and it's going to double bond to this oxygen, but don't draw your carbon dioxide like that. That looks terrible. Redraw it to show that there's a double bond to this oxygen and a double bond to that oxygen. So carbon double bonding to oxygen, double bonding to oxygen. Okay, this is how I would draw carbon dioxide. It is a linear molecule, okay? And I show that it is linearly, okay? Now this is my Lewis dot structure, okay, of my example. If I wanted to draw it, literally they call it a ball and stick model, okay? You got it, just like this, okay? If I wanted to draw out that ball and stick model, okay, I literally show I've got my central atom, and coming off of my central atom is an atom over here and an atom over there, okay? That shows me a linearly bonded molecule, okay? Shoot, and I didn't include angle, which I should. All right, so the angle from one atom to another here is going to be 180 degrees. All right, we'll just write angle in here as well. So model and angle. All right, so this is my easiest possible molecule, okay? Next, okay, try to kind of squish that in so we can just continue on, okay? So next, all right, if I was going to add another atom to my molecule, okay? So another atom is going to bond to my center atom, okay? If I do this, all right, remember that all of these electrons repel each other. They want to be as far apart from each other as possible. So these guys are going to kind of like, oh, dear God, this is way too close. Okay, I need to squish away from him. So they're going to try and angle away, all right, from that third atom that joined. Okay, and now you kind of have this like, you know, peace symbol, all right, Mercedes symbol if you're swanky, all right, that all these atoms are as far apart as possible, because if this guy went any closer this way, then he's, you know, too close to this other atom, so he's going to repel this way. If he goes any closer this direction, he's going to run into here, okay, so he's going to repel from that atom. You might think, well, there's all this space up top, right? If I was going to angle it like this in the camera, right, there's all this space up top. Well, why doesn't this guy just come up this direction? Okay, and that's a good idea, but now look, okay, if he comes up towards the top of that molecule, the way that we initially had it oriented, now these two guys are closer than what they were before, right? So the furthest away that these guys can be, that these valence electrons can be, according to VSEPR, is by forming this, you know, peace symbol situation, okay? They're all as far apart as they can be, with 1, 2, 3 atoms bonded to my central atom. So instead of 2 atoms, we're going to up the ante. Now we're going to have 3 atoms. And again, no lone pairs yet, okay? So my total electron groups, I have 1 group here, 1 group here, 1 group here. 3 total groups. And again, these guys added up should be my total electron groups on my central atom, okay? So now, what shape does this take for my electron groups? Okay, so now we're just kind of looking at the toothpicks, all right? What shape do my electron groups take? Well, they are as far apart from each other as they can be, and they're on the same plane, right? So this is a flat molecule. All these electrons are, can I angle this so you guys can see this on the camera? Okay, ish. These are flat, right? There's nothing sticking up or underneath. Okay, they are flat, so they're on the same plane, and there's 3 of them, right? So this electron geometry we call trigonal, or trigonal, if you, okay, want to pronounce it like trigonal, and it's on the same plane, so planar. Which just means there's 3 things, tri, right? So it's 3, like a tri, you know, a decagon, a pentagon, hexagon. This just means shape, right? So it's trigonal. So the shape has 3 things, and it's planar. It's on the same plane. It's flat. All right, and that's for my electron geometry. Now I'm looking at my molecular geometry. So you're actually looking at the atoms now. Well, the atoms take the exact same shape, right? So this is also going to be trigonal planar, however you want to pronounce it, okay? And a real life example of this lovely one would be CH2O. So if I was going to draw out CH2O, carbon has 4, each hydrogen has 1 single, and oxygen has 2 singles to bond, okay? So my carbon's going to be in the middle, bonding to a hydrogen, bonding to another hydrogen, and then double bonding to an oxygen, right? Okay, this would be my Lewis dot structure for a real life trigonal planar situation, okay? And if you can see, right, from my central atom, there's 1, 2, 3 electron groups. 1, 2, 3 atoms that are bonding kind of in a, you know, Mercedes formation, okay, peace symbol formation. If I angle that correctly, okay. All right, if I wanted to draw the ball and stick model, here's my central atom. I'm gonna have one atom coming up, one atom coming over, another atom coming over, okay, like that. And this angle would be 120 degrees, okay, 360 divided by 3, 120. So all of these atoms are 120 degrees away from each other. All right, now we're going to add another atom, right? So instead of 3, we're gonna have 4. And I'm gonna need new pages, so hold up. Okay, so this will be the last quote unquote easy one, okay? So instead of 3 atoms bonded to my central atom, I'm going to now add another one. So I'm gonna have 4 atoms bonded to my central atom, all right? But what I want you to see happen is what's going to happen with these molecules, right? With these atoms, because if I added a 4th one, okay? If I add it like up top, all right? Now these guys are really close, okay? And they don't want to be close. So our 3 initial guys, one fell off, okay? Our 3 initial guys are going to try and angle downward from the 4th one that we just added up on the top, right? Because this guy is not going to be added on the same plane. If we did that, then all these atoms can only be 90 degrees apart from each other, right? This is really close. These electrons hate each other. They're going to try and repel each other and push each other away, okay? So my molecule, my atoms are going to kind of shift, if you will, if you can think about this, okay, to be as far apart from each other as possible. So in order to do that, okay, let me try and get it back to what it was before with my trigonal. All right, so here's trigonal planar, right? If my 4th guy comes up and just kind of adds up on top, then these 3 guys that were in the same plane, right? 1, 2, 3 in the same plane, they're just gonna angle away from him. So basically be attached to the same part, but just angle away. Like, gosh, I don't wanna be that close to you, okay? Everybody likes their own space. All right, and if I did this correctly, all right, and they angle away, then it should be, all right, whatever 3 I have at the bottom, okay, whatever 3 that I now have at the bottom, the 4th one's going to be pointed straight up. And it should not matter, perfect, okay, which 3 I put at the bottom, that 4th one points straight up. Let's cover up the old one there, okay. All right, so not quite angled correctly, okay? But if you can tell, all right, this is now a fully 3D situation where, you know, an atom is going to be pointed straight up with the other 3 angled slightly down, okay? So can everyone see that? I know it's difficult to see this on a kind of 2D screen with a 3D molecule, okay? And let's fill out our table, okay? So if I have 4 atoms bonded to my central atom, right? 1, 2, 3, 4. No lone pairs yet, okay? Total electron groups, 4 plus 0 is 4, okay? Or you could just look, right? 1, 2, 3, 4 electron groups coming off of your central atom, right? Now my electron geometry and my molecular geometry are gonna be the same again, because no lone pairs yet. Okay, and this, I have 4 different directions, okay? So the prefix for 4 is tetra, and then this is a 3D shape, so it's a hedral, so a tetrahedral, okay? And my molecular shape is gonna be the same. 4 atoms bonded to my central atom going off in those 4 different directions, tetrahedral. All right, this is a tetrahedral molecular shape. And a real life example of this would be CH4, okay, methane, right? So if I was going to, get that out of the way, if I was going to draw out methane, okay, if I was going to draw that out, this is typically how methane is drawn out, okay? Carbon with 4 hydrogens going around, all right? and it kind of looks like it's flat. In real life, this is not what methane looks like, okay? It is a 3D shape, right? So you can imagine if this was the hydrogen up top, these hydrogens here are going to angle downwards, okay? So this is like the easy way to draw it. I would never mark you off if you drew it like this, but in reality, nope, you won't be able to see that, okay? Carbon's here in the middle. This hydrogen comes up top, all right? Now this hydrogen kind of has a wedge out, like it's coming out towards you, all right? This hydrogen has this little dashed line, like it's going backwards into the page. And then this hydrogen is on the same plane as my top hydrogen. So if I can attempt to show you that, okay? So these guys, right? This hydrogen up top and this hydrogen off to the left, right? Those are in the same plane, okay? This guy is coming out at you. Oh, coming out so far at you that, there we go, that I ruined the model, okay? So this guy's popping out at you. So there's my little wedge. He's coming out at you. This guy's going into the page, okay? Dash, 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 going into the page. So you can see that this is showing me that it's a 3D shape, okay? If you hate the 3D situation with like dashes and wedges, I don't blame you. Don't freak out, okay? But if you were gonna draw the ball and stick model, okay? Got my central atom, and you could just kind of do it this way. One atom up, and then just kind of show that they're angled down, right? You could totally do it like that, that you're showing that it's not 90 degrees exactly, right? Because it is, in fact, 3D. And by all means, if you want to show, here's a wedge, and here's your dashed line, you can do that, okay? Kind of looks wonky. You get it. And my angle for this guy is 109.5 degrees, okay? All right, on we go. So now it starts to get interesting, okay? Because instead of adding another atom to my central atom, instead what I'm going to do is replace one of them with a lone pair, okay? So imagine instead of this being an atom, it's just going to be a lone pair of electrons, okay? So these are still gonna represent electrons, but it's a lone pair on my central atom, okay? So now, if I'm looking at my table that we're making, okay, nothing really changed, not too much, about my actual shape, okay? All I did was just replace the fact that these electrons, instead of bonding to an atom, are now just lone pairs, okay? So how many atoms are bonded to my central atom? 1, 2, 3 are bonded to the center, right? So 3 atoms are bonded, and now how many lone pairs are on my central atom? This little toothpick is going to represent 1 lone pair of electrons, okay? So total electron groups is going to be these two guys added together, okay? 3 plus 1 is 4, all right? And you can look, 1, 2, 3, 4 electron groups, right? 4 toothpick directions that electrons are going from your central atom, okay? So now your electron geometry, all right? Well, what shape do all of your electrons take? They take the same shape that we had before. They take a tetrahedral shape. Your electrons are still going to be in that tetrahedral shape. However, okay, this is where it actually gets interesting. When your lone pair is not 0, you're going to have a different molecular shape than your electron geometry, okay? And you can tell, right? The electron geometry is not tetrahedral. And it's also not trigonal planar, okay? These 3 atoms are not in the same plane. This is not a flat molecule anymore, like it was for, you know, our flat trigonal planar situation. So instead now, what this kind of looks like, if you can see that, okay, it kind of looks like a pyramid. And that's exactly the shape that we call it. We call this pyramidal. So this shape is a pyramidal shape. And the most common example of that would be ammonia. So if I was going to draw out NH3, nitrogen has 5 valence electrons, one lone pair, and 3 singles, right? And 3 H's. So I'm going to bond H, H, and H, okay? Because I have this lone pair instead of another hydrogen, for example, like CH4, right? I don't have another atom coming off here. Instead, I have a lone pair. So I force these 3 hydrogens to take this pyramidal shape, right? Like this. And I still have this lone pair up at the top, okay? So if I was going to draw my kind of ball and stick model, right? Here's my central atom with, kind of angle it, right? 1, 2, 3 atoms around it. And don't forget that you have a lone pair. Okay, so make sure that you are drawing in your lone pair, your 2 electrons, okay? We draw it with this kind of like, you know, orbital shape. There you go. See, so you can see that kind of orbital shape is showing your lone pair, okay? Because your lone pair, your 2 electrons are going to be in an orbit together, right? In an orbital together. So this would be your ball and stick model, okay? And the angle that these guys take is going to be about 107 degrees, okay? Because those lone pairs are slightly closer to the central atom than if it was bonded to another atom. So it smushes those 3 other guys slightly closer together. All right, so if this was a true tetrahedral, it would be 109.5 degrees away from each other. But since it's pyramidal and these lone pairs just kind of squish them down a little bit more, it's 107. They're just slightly closer together than they would be if it was tetrahedral. Only one more to go. Okay, we're almost done, I promise. I'm going to do the exact same thing. So instead of adding another atom, what I'm going to be doing is replacing one of my atoms with a lone pair. So instead of, for example, this guy bonding to an atom, instead of these electrons bonding to something, taking the atom away, and now it's another lone pair, okay? So I only have 2 atoms bonded to my central atom, but I also have 2 lone pairs bonded to my central atom. So I have 2 atoms bonded with 2 lone pairs, okay? Total electron groups, again, these 2 numbers added together, right? 1, 2, 3, 4 electron groups, okay? 4 different directions that electrons are heading from this central atom, right? 4 directions that the electrons are going. And my electron geometry is again still tetrahedral, right? Electrons are heading off in this 4 different directions, tetrahedral, okay? But now my molecular geometry is very different, okay? I only have 2 atoms bonded, but this certainly is not a linear molecule like CO2 was, right? This is now not linear. It is in fact bent. And that's what we literally call it, okay? We call it a bent molecule, okay? And the most common one for this would be water, and probably the most important ever, okay? I'm just gonna get rid of this guy so we have space. All right, so this is gonna be my drawing for water, right? So if I had H2O, right? Oxygen, and this is another reason I want you to learn to draw those Lewis dot structures, right? With your valence electrons in a circle, okay? So oxygen should have 6 valence, 1, 2, 3, 4, 5, 6. So I'm showing that I have these 2 lone pairs that are kind of next to each other, if you will, okay? Not across from each other. Then I have 2 hydrogens that are going to bond. So hydrogen here and hydrogen here. This is what water looks like. If I was going to do ball and stick, central atom, 1 guy, 2 guy, and then you have 1 lone pair, 2 lone pairs, okay? Literally exactly like this, all right? And again, since there's 2 lone pairs, it kind of squishes those guys even closer together. Instead of 107, it's going to be about 105 degrees, okay? All right, now it's really important that you understand this. And again, this is why I want you to get used to doing it in a circle, okay? Because if you're doing water and you just go H bonded to O, bonded to H, done, and then there's 2 lone pairs and you do it, oh good, that's off the page so you can't see it. Okay, if you just drew it like this, okay, you'd be like, oh good, this is linear. And then you'd be super wrong. okay? Because water is not a linear molecule. It is a bent molecule, okay? This thing is a bent molecule because it has those two lone pairs, okay? This is not linear. This does not look like carbon dioxide. I was going to draw it again, but I don't want you to get confused, okay? So please make sure you're very careful with figuring out your molecular shapes, okay? Your molecular geometry. All right, water is a bent molecule because it has lone pairs, which is actually really important. That has to do with hydrogen bonding and why water is a liquid at room temperature instead of a gas, which is why we're all able to live on this wonderful planet. So, all right, so that's the VSEPR model, okay? In general, all right, VSEPR model just means your electron pairs want to be as far away from each other as possible. You know, valence shell electron pair repulsion theory, VSEPR. Yuck. Okay. Woof.